So in this video, we're going to talk about graphing some of the trig functions that we talked about in the last video. So this is an applet that's available for free online, and I'll post this link in our page as well. And notice we're going to start by talking about this unit circle right here in the center. This is the same unit circle that we were looking at before. And we see I can drag this point and it will change the angle that's displayed. And this display is given in radians. So we see that right at a 90-degree angle, we have pi over 2 radians. And when we go a full 180 degrees, it says 3.15, but that's pi radians for this half circle. So what we want to look at is what happens when we want to graph a trig function. Let's set our angle down close to 0. That's about 0. And I'm going to highlight over here the sine function. So along this graph, we see a sine function being traced out. What exactly is being represented here? Recall that sine is the height, the vertical length of this side of the triangle. That sine is given by opposite over hypotenuse. In this case, our hypotenuse is exactly equal to 1. So it's measuring the height of this green side. And the inputs are this angle in radians. So notice as I drag this and make this angle bigger, on this graph, the angle is being measured along the x-axis, and the height of the green side is being given along the y-axis. So I can increase my angle until I get all the way to pi over 2, which is 90 degrees, and we see that the green height of the triangle is exactly 1 because my circle has radius 1. And continuing on, as my angle gets bigger and bigger, you see that the green side length gets smaller, and then the green side goes down negative. So this graph is a visual display of when I put an input of an angle in radians, it's telling me what is the height of the green side of this triangle along the unit circle. Or in other words, it's giving me an output of the sine of that angle. Let's take a look. Let's move the angle back to 0 again. And when I click on cosine, this is giving me a slightly different function, but the same sort of idea. Notice that now my angle in radians is about 0. In degrees, it's also about 0. It's flat. Cosine measures the length along the bottom of the triangle. So my input, again, in this graph along the x-axis is radians. And my output, instead of being the green side of the triangle measured vertically, it's the width of the triangle measured horizontally. So as this angle gets smaller, notice this red length gets smaller because the bottom of this triangle, or the x-coordinate of this point, is getting smaller and smaller until my x-coordinate of the point becomes negative, and again it goes around in a full circle. And you can trace this unit circle and it will give you a readout of the points along this graph. Well, and we can put both on top of one another. This visually looks a little confusing, but it's saying that for when I trace this, for this given angle, I have on the green function is my sine function that's giving me the height of the triangle, and the red function is my cosine function. It's giving me the length of the base of the triangle, and they're lining up right at that given angle. So this applet lets us do, maybe I'll do one more thing. Let's leave the sine and cosine functions up. I'm going to add the tangent function. Ugh, now everything's getting crazy. Maybe I'll take one of the functions away. So recall for the tangent function, it's the ratio of sine divided by cosine. So I can look and see what's going on. My tangent values are shooting off towards infinity, and it's because we have all of these vertical asymptotes. These vertical asymptotes take place because tangent is a ratio. It's the ratio of sine divided by cosine. If my cosine function is equal to 0, we know that our tangent function is going to head towards infinity. Let's look at where that is on the graph. So when my cosine function is equal to 0, that's when, if you notice, It's when the red bottom of this triangle is getting smaller and smaller and smaller and approaching 0. It means that my sine function is getting closer to 1. So my value of tangent at that point is going to be 1 over 0, which is undefined. And we can see visually it's actually represented by the length of this tangent line. And you can see that as you drag this point, that tangent line is going to get longer and longer and longer until right at a 90-degree angle, this tangent is infinitely long, right? It's never going to intersect this bottom line down here. And then as I go back the other direction, we see that it shoots back to the negative side, and this is a visual representation of tangent in the other direction. All right, let's talk about the remaining graphs on here. So here's my sine function again, measuring the height of the triangle, or my y-coordinates of the unit circle. I'm going to look at this function, the cosecant function. This is something that I want to recall. This is something we didn't bring up in the last video. These are a set of reciprocal identities that you might want to mark down if you don't have them memorized already. That we can recall that sine is the ratio of the opposite over the hypotenuse. And if I wanted to, what if I wanted to flip that and consider the ratio of the hypotenuse over the opposite side? I could just take my sine function and flip it upside down. And that's exactly what cosecant is given by. So cosecant is just the reciprocal of sine. I'm just flipping it upside down, or taking 1 over my sine function. Similarly, I have cosine, and if I want the reciprocal of cosine, I get secant. And then finally, the reciprocal of tangent is cotangent. And we can examine those graphs here also. I'll put sine and cosecant on the same graph. Whoa, things got a little crazy, right? The sine function again was the green original, and we see that when our sine function goes to 0, 1 over 0 is going to be undefined, so we get these asymptotes again. And when this unit circle is measuring, this is a cool visualization of what the cosecant is. It's going to be exactly the distance. If I were to make another right triangle, it would be the hypotenuse of that triangle where the hypotenuse is exactly vertical. Or thinking about putting a tangent line on this circle, it's going to be the height of the y value of that bigger triangle. And you can play with this yourself. And so this orange dotted line is given by the output for a given angle, gives me my cosecant function. Here's my cosine. Here's my secant. Again, we have the same asymptotic behavior, and that's also displayed on this triangle. And finally, we have tangent and cotangent, and they're essentially mirror images of one another, also with the same asymptotic behavior. Next, I'm going to pull this view over a little bit so we can see what these functions look like. There are other things on this applet that we can mess around with that I want to mess around with a little bit. We have this H slider, the K slider, the B slider, and we actually have another slider. If I wanted to, I want to shift or manipulate this sine function. Right now, this sine function is a periodic function, and that's because it repeats itself. It goes an upper hill and a lower hill and back to 0 every 2 pi. Then I repeat that pattern again and again and again. But I can shift the period. I can shift this function in a number of ways. One way I can shift it is I can stretch out the amplitude. So that's making the function taller and shorter. Let's see how that looks algebraically, and also how can I manipulate this graph to do that. So I'm going to drag, right now this is a unit circle, that the height of the circle goes up to 1, and that's why this graph goes up to 1. I can, oh, maybe I drag on this side. Yeah, if I take this corner and drag it, let's say I wasn't working with a unit circle anymore. Let's say I had a circle of a radius 2. So now, as I trace out my sine curve, I see that it's the same shape, but I've just stretched it taller because the circle that I'm tracing out, my basic circle, is no longer a unit circle. And if I look over to the algebra view of this function, oh, I guess I didn't stretch it out quite to a radius of 2. I stretch it to, here's about a radius of 2, right? So this is telling me that when I have a coefficient on front of my function, it's going to elongate the amplitude, or stretch it taller and shorter. There are other things that I can do to manipulate the function. Let's go back to our unit circle. That's close enough. We don't want to mess around with too many things at once. Another thing that I can do is my k value, oh, you can't quite see it on this, plus k. So my k value, I can add and subtract just a constant at the end of the function, and that's just shifting it up by 3.6 is where I've left this slider at for k. And that's exactly the same thing that you could do to a parabola. If this was some messy function of a parabola and I decided to add 3.6 to it, it would just shift the parabola vertically by 3.6. That's one shift that is easy to visualize. Another shift that we could do here, I'm changing h. What is h doing in this? So let's make an h of 2.1. Essentially what I'm doing is I'm shifting where my x values are inputted. Typically the x value is representing the radians, and normally when my radians are 0, I'm looking at the sine of 0, which is an angle down here. Now when I input 0, instead of looking at the sine of 0, I'm looking at the sine of negative 2.1. So I'm moving, wait, I should just leave that angle still. This was my h value. So by changing, adding and subtracting things right in next to this x value, it's going to shift where this sine graph lines up with the x-axis. And then the final slider that we have on here is our b value slider, and the b value is the coefficient on our x value. And what's going to happen then? The coefficient within the sine function is going to make the function have a faster period or a slower period. As the value in here gets higher, what's this saying? This is saying that I'm essentially going around this circle 3 times faster than I used to. So let's go back to where b equals 1. Whoops, b equals 1. Here's the normal pace of a sine function. It does 1 period for 2 pi. And then if I make it go twice as fast by adding a 2 on the inside, twice as fast gives me 2 periods within a 2 pi distance. And if I want it to go 4 times as fast, shoom, shoom, shoom. Now I can see 4 periods, 1, 2, 3, 4 within the 2 pi distance. So hopefully that's a brief overview of some trig functions and their graphs. And this is a great applet to play around with to improve your own intuition about how to manipulate sine, cosine, tangent functions to give you a visual representation of what those functions look like.